let's get started, please. Let's get started, please. So 17.5 is got these things called div, grad, and curl. Actually, there's a book called Div, Grad, and Curl, Div, Grad, and Curl, and all that. So if you want, you can look up this book. It's by somebody whose last name is, I think, Shea. Okay. So so we're going to start off with just a notation, and that is. We're going to use this upside down triangle, or I guess it's just a triangle, to denote this thing. Partial with respect to x, partial with respect to y, partial with respect to z. Okay. So it is a, you could call it a vector differential operator. And people usually call it the, called the del operator. So this is not, it's not a vector, right? It's not a vector. It's, you know, it's some sort of like vector with, instead of numbers here, it has these differential operators. Okay, so it's not a vector, but you pretend it's a vector, and it turns out to be a convenient thing. Okay. So we're going to introduce an idea called the curl of a vector field. So given f from R3 to R3, a vector field, we define the curl of f. Okay, so curl of the field. Okay, and what this means we'll clarify shortly as something like the vector, the del operator across the field, using the notion of cross product from before. Okay. So you know what this is this. So we've got the del operator here, and then f1, f2, f3. So right, it actually doesn't make any sense to talk about to put these things inside the matrix, but you do anyway as a sort of mnemonic device. Okay, so this is just a mnemonic that you use to calculate it. Okay, so you're going to take right. So you take df3 dy minus df2 dz, and that's in your so what's this going to be? Right, this is going to be df3 dy minus df2 dz, comma, and then negative df3 dx minus df1 dz, comma, and then df2 dx minus df1 dy. Okay, so you see how. So this is the definition of the curl right here, and it's easier to remember using the del notation. It's going to be the del operator across the field. Okay. Okay. So for example, right, if I give you a field f of x, y, z being e to the x, e to the xy, e to the xyz, so you have some field, then the curl of that field, you're just going to calculate, as we just did, right? Partial with respect to x, partial with respect to y, partial with respect to z, u to the x, u to the xy, e to the xyz, right? And you get, well, you get the derivative of this thing with respect to y, so it's going to be xz e to the xyz, minus the derivative of this thing with respect to z, which is 0, right? You get negative the derivative of this with respect to x, minus this guy's derivative with respect to z, which is 0. And then you get ddx of this guy, which is y e xy, and then ddy of that, which is again 0. Right. Okay. So from one vector field, you get another vector field. Okay, and this guy is called the curl of the first guy. Okay. Okay. Any questions on how that's calculated? Pretty simple, right? Okay. It's just you just have to remember it. Okay. Another example. If you have a field that is in R2, so this field is in R2, normally, and you want to talk about the curl, what one does is we, in this case, one considers this as xy, x squared y, 0. Okay. So you basically embed the field into R3. You make an R3 field out of this field. Okay. Okay, and then you do as before. So you have this field, it's a vector field on R2. You'd like to talk about its curl, so you embed it in R3, and then you take the curl. So, and do as before. Okay. So what do you get, right? You're going to end up with, again, ijk, ddx, ddy, ddz. And then xy, x squared y, 0. Okay. But you see what happens when you do that, right? You're going to get I ddy of 0 minus ddz of x squared y. Well, that's just 0, right? Because you're taking the derivative of 0, and you're taking the derivative of something in x and y with respect to z. Well, that's just 0, right? And then the second term, what's going to happen? Well, you're going to get ddx of 0 minus ddz of xy, right? Again, you're differentiating something that depends only on x and y, so you get 0 again, right? And then the third guy, what are you going to get? You're going to get ddx of x squared y minus ddy of xy. Right, that's to say 2xy minus x in this case. Okay. So, right, so when you have a field in R2 and you calculate its curl, you're always going to end up with 0, 0, and then something. Okay, so now think, and notice. Let's just write this ddx, ddy, ddz. So if you have this field p of xy, q of xy, comma 0. So, right, say that f of xy is p of xy, q of xy. Right. Okay, and we're going to take this R2 field, we're going to stick it into R3, and we're going to take the curl of it. Okay, what do we get? We're going to get 0, 0, and then dq dx minus dp dy. Right, dq dx minus dp dy. Okay, does that look familiar? That should look familiar, right? That's something we saw last time. That's the thing that we integrate over the interior to get the integral, to get the circulation on the boundary, right? Circulation of the field around the boundary, right? So so we can using this notation, we can rewrite or rephrase Green's theorem to read like this: the integral of the field around the boundary is the same thing as the curl of the field dotted against K dA. Right, where K is 0, 0, 1, right? The upwards normal vector. Right? Okay, so the circulation of the field around this loop is the same as the integral of part of the curl. This thing is called the scalar curl. The scalar curl. It's the scalar curl of the field on the interior. Okay. So in fact, this gives a physical meaning to Green's theorem. So physical interpretation. Okay. So in fact, the curl is something that that describes rotation of the field. Okay. And if you want, again, if you want the details, I suggest go look at that book. They'll sort of describe how you do this. So the magnitude of the curl corresponds to twice the angular velocity. And the direction of the curl is the axis of rotation of an object via right-hand rule. Okay, so there's actually a physical meaning to this thing called the curl. If your curl turns out to be some vector, right? You say, the curl is a vector field, right? And so at every point, there are all these vectors. And what it tells you is if you took some sort of like small fan-like thing and you put it there, right? What would happen to that? What would happen to it? Like how it would start if it's right. Suppose you you have like a stream, Okay, and the stream is doing stuff, and you put some sort of object there, and you fixed it there. The curl, what the curl tells you is how fast that object would be rotating, right? So 1/2 the magnitude is the angular velocity. It tells you how fast that thing will be rotating, and this tells you in which direction to be rotating. So it says in the direction of the curl, you're going to be spinning around it in this right hand roll direction. Okay, so this is the information, the physical information contained in the curl. If you're using your vector field as a description of the velocity of some fluid, say. Okay, so you have some gas or you have some liquid, right? And you know, this tells you about the spinning at each point. Okay. And so what that tells us then, that gives us like an interpretation of this, of Green's theorem. Right? It says that to get the rotation, right? So we're taking the remember what this is. This is the field dot the unit tangent vector ds, right? It's the same thing as this. Where in calculating the integral of the field dotted against the tangent vector, it suffices to take the sum of the curls. So you take the sum of the curls on the interior, and that will give you the circulation of the field around the boundary. Okay. That's the interpretation of Green's theorem. That the circulation of the field around the boundary is the integral of the curls on the interior. So this leads to one definition, which is if the curl is 0 everywhere, we call the field irrotational. Any questions so far? Right. Nothing fancy. Right. All we've done is said you have a field. You take the cross product of the field with the del operator. You get this thing called the curl. The curl contains certain information. Right. And if in 2 dimensions, we see that Green's theorem can be rephrased in terms of the curl. Okay. Like you might have been wondering, what was that? dq dx minus dp dy. What was that? Right, it seems sort of mysterious, but now you see it's actually the scalar component of it's the curl. Okay. Second important notion is divergence. Something called divergence. And again, I'm going to define it for you just mathematically first, and then later I'll give the physical interpretation. So when R3 to R3, you have a vector field, and let's say that say f x, y, z equals p q r. Then the divergence of f at some point, right, is defined as partial of p with respect to x plus the partial of q with respect to y plus the partial of r with respect to z. Okay, and the mnemonic is that this is the dot product of the del operator against f. Right? Remember, the del operator is this ddx, ddy, ddz. Right? And we take that thing and we dot it against pqr. Right? right? So, again, doesn't make sense to talk about, this. We're not really multiplying, right? To talk about a dot product means that you take the product of this thing and this thing. So it's very much a lie, right? To say that this is right, but we do it anyway. Okay, it's a useful mnemonic. Okay, and so you see what you do. You take the partial of this guy with respect to x, and the partial of this guy with respect to q, partial of this guy with respect to z, and you add those things together and you get some number, right? So this to each point you associate some number, not a vector. It's a scalar. It's what's called a scalar field. Scalar field, or more simply, a function. Right? To each point it associates some value. It's not a vector field. Okay. Okay. So again, example: if I let f of x, y, z be x squared y, x z, x, y, z, well, then the divergence of that guy is going to be the partial of this with respect to x, partial of this with respect to y, partial of this with respect to z, I get 3xy. Right? If I have some field negative x, negative y, then this is going to be partial with respect to x plus the partial with respect to y. You get some constant. Right? It's constant divergence. Here the divergence depends on x and y. The farther away you are from the origin, the bigger in magnitude the divergence. Okay, so there's a second thing called the divergence. Again, let me give the physical interpretation. Does that make sense? Right? I mean, there's not much to make sense. All it is a notation. We just introduced a notation. The divergence is the sum of these partials. Okay. The physical interpretation is that divergence is the ratio of flux to enclosed volume, or tendency to flow inward when the number is negative, or outward when the number is positive. Okay, so the idea is like this: you take a tiny box, okay? You take a small box, and you put it in the gas, okay? And what you measure is if the divergence is negative there, then that means that gas is flowing into the cube. Okay, more gas is flowing in than is flowing out. If it's positive there, then more gas is flowing out than flowing in. Okay, and the ratio of the flux, that is how much is passing, the total of how much is passing in and out over the volume of the cube, is the divergence. Okay, so it tells you, how much, proportionally how much gas is coming in or coming out of the cube. Okay, so that's what divergence is. Again, this interpretation leads to the following terminology. If the flux is 0, we say the field is incompressible. the field is incompressible. You can't, right? You can't compress it. Okay. So, for example, it's my understanding that water is an incompressible fluid. That is, if you have something in the water and you try to push a certain amount of water into that cube, well, it's going to come out the other side. That same amount is going to come out, right? So there's the amount that's going in is the same as the amount that's going out. The divergence is always going to be 0. Okay, you're never going to have you can't you can't like have more water going in that's coming out of that cube. I think that's almost true. It may not be completely true, but it's pretty close to true. That is, I think water is slightly compressible, basically incompressible. So we haven't done too much. All we've done is introduce some notions. We'll continue to not do too much for a few more minutes. Often I ask at the end of the term what was the most exciting or beautiful thing that you've seen in the course. But I think maybe it's also interesting to ask what is the least impressive thing that you've seen in the course. In the last class, I did something that basically involved elementary school fractions, like using a common denominator. That is when you do L'Hopital's rule and you do the indeterminate form infinity and minus infinity. The trick is basically use a common denominator. So that was like maybe the least impressive thing that they'd seen for at least a day or two. But anyway, okay. Okay, so we've introduced these two notions, okay, and now we're going to make some observations. Commonly made observations. Okay. These observations are sort of interesting, but not particularly exciting. They're not hard to see. There's nothing complex in their proof, I'd say, in their demonstration. So you have a function that is that's twice continuously differentiable. Then if you take its gradient field and you take the curl of the gradient field, then it turns out that the curl is 0. Okay. In other words, gradient fields are irrotational. Gradient fields are irrotational. Okay. The proof is, right, what do you have to do? We have to see that this thing,
Sorry.
function,
What's that, sorry?
C2 function,
C2.
C2, that's a C. I was debating whether to use a cursive C, cursive like C, or a normal C. And I got caught halfway between. Okay, so the proof is we just calculate, right? So we take the curl of the gradient. I'm going to use the big D notation rather than the curly little d notation. Okay, and you see what happens, right? In the first variable, what do you get? d2, d3f minus d3, d2f, right? Which is 0, right? And then second one, you get d1, d3f minus d3, d1f, which is 0, right? And in the third, you get d1, d2 minus d2, d1f, which is 0, right? what you're using is that mixed partials are equal as long as your function is C2. In other words, so-called Clairaut's theorem. Right? So by Clairaut's theorem, we know that this is going to be 0, the vector 0. Okay, so any gradient field is irrotational. So, okay. In fact, there is a converse statement. In fact, the converse statement is true. If you have a C1 vector field, and the curl of f is 0, then in fact f is a gradient field. Okay. And we're not going to give the proof of that. So say you have this C1 vector field. If its curl is 0, then it turns out to be that it's a gradient field. Okay. So any irrotational field is going to be a gradient field. Any gradient field is going to be irrotational. So this gives you a way of checking. One can thus check if a field is conservative by taking its curl.
So there's no field that if the curl is 0, then it's not the gradient.
That's right. That's right. So if its curl is 0,
It has to be.
it has to be a gradient field. Well, as long as it's sufficiently smooth.
Okay.
So yeah, but basically speaking, anybody whose curl is 0 is a gradient field, and vice versa. Okay. Okay. So for example, if I give you a field f of x, y, z equals y squared z cubed, 2xy/z cubed, 3xy squared z squared, and I say, is it conservative? Do you have a question, Sydney? Yeah. I say if it's conservative, well, one way to do it is to just take its curl. So you'd say, okay, I, J, K, d1, d2, d3, y squared z cubed, 2xy z cubed, 3xy squared z squared. Right? And then you'd say, okay, well, I'm going to get a derivative with respect to y of that 6xy z squared minus derivative with respect to z of that 6xy z squared. Right? I'm going to get derivative with respect to x, 3y squared z squared, derivative with respect to z, I get 3y squared z squared, and right, derivative of this guy with respect to x 2y z cubed minus derivative of this guy with respect to y 2y z cubed. Right? You say I get 0, 0, 0, and so I know that this guy is conservative. Okay, so that's one observation about gradient fields and rotation. There's a similar sort of thing that one can see about dealing with compressibility. So you have a C2 vector field. Given this C2 vector field, then the divergence of its curl is always 0.
Can you quickly explain the difference between a C1 vector field or a C2 vector field?
It just means that the component functions are differentiable, continuously differentiable up to the second order, up to what order? So here, the component field, the component vectors, component functions, right? So this is x, y, z goes to f1, x, y, z, f2, x, y, z, f3, x, y, z. Right? And all it's saying is that f1, f2, and f3 are their first derivatives are continuous. Okay. And here we're saying that the second derivatives will be continuous. Okay, so what this is saying is that, roughly speaking, that curl fields are incompressible. Right? In English, that's what it's saying. The curl of a vector field has divergence 0. Okay, and then the proof of that, it's just another calculation, sort of like this calculation. So I'm not going to do it. Okay, and then there are other identities that maybe are useful in physics or something, but it's not going to be that useful for us in this course, but except as maybe homework problems. If you take the cross product of two gradient fields, the divergence of such a thing is 0. If you take the curl of a curl field, that's the same as the gradient of the divergence minus del squared f. Anyway, don't worry about it. There's a bunch of identities that hold true. The last thing in this section that is interesting, and actually this really is interesting, is two forms of Green's theorem. Okay, so we have one, right? We have one form that if you take the circulation about the boundary around a closed curve, then that equals the integral of the scalar curl over the inside, right? Okay. So this is called the circulation curl form of Green's theorem. There's another.
Explain what the K is again.
The K is 0, 0, 1. Right, so you're just taking the dot product of this thing, right, which was 0, 0 dq dx minus dp dy, right? And then dot against 0, 0, 1. There's a second form, which is called the flux-divergence form. And it goes like this, that if you take the field dotted against the outward unit normal vector, then that's the same as the divergence, the integral of the divergence over the interior. Okay, so the picture you have here is like this, right? So here, right, we're integrating f dotted against the unit tangent vector, right? So at every point, you've got this unit tangent vector, unit tangent vector, unit tangent vector, right? You've got these unit tangent vectors going around. You take your field dotted against the unit tangent vector, and then sum all those things over the edge, and that is the right. That's the same as the integral of the curl over each point over the interior. Here, what we have is, at each point, you have the outward unit normal. So it's going to be perpendicular, right? Perpendicular to the surface, perpendicular to the curve, and of norm 1. Okay. And at each point, you take f dot that, right? So you've got all these guys, right? Right, you take f and you dot it against each of these guys, and then you take the integral of that against arc length. Okay, and that tells you that turns out to be the same thing as the integral of the divergence. So remember, the divergence measures, like, at each point how much you're going in or out. So at each point, you have these divergences, and you take the sum of the divergences. The total divergence over this interior is the same thing as the flux through the boundary. Total divergence is the same. Total divergence is the same as the flux through the boundary. Let me give an example of how this happens. So f of xy, let that be 2y, comma, minus 3x. Okay, and let C be the unit circle. Okay, and our question is, what's the flux across C, right? What's the flux of F across this thing? Okay. So if you want to calculate it, right, we can calculate it in the standard way, right? It's a line. It's defined. The flux is this line integral, and so we can do it. You say, okay, let R of t be cosine t sine t. right, as t goes from 0 to 2 pi. In that case, our prime t is going to be negative sine t cosine t, right? And so that's the tangent vector, right? Right? That's the tangent vector. And what's going to be our unit normal, right? The unit normal is going to be perpendicular to that, right? And going outwards. It's going to be cosine t, sine t. Cosine t, sine t again, right? Here you've got this, right? The unit normal is going to be pointing outwards like that, right? Right. You can one way of getting the unit normal is to take the unit tangent and then just reverse these guys and put the minus on the second one. See? Right? Because then you'll get something perpendicular. You'll get something perpendicular to the unit tangent. Okay. In any case, so what's this integral? It's going to be the integral from 0 to 2 pi of my function, right, evaluated at r. My function evaluated at r of t dot n times the magnitude of r prime dt. Right? Which works out to be my function evaluated at r of t, so that's going to be 2y minus 3x dotted against cosine t sine t times the magnitude of r prime, but that's just 1 dt. And you work it out, it turns out to be 0. Okay. But you could also use Green's theorem and say that the flux across the boundary is the same as the divergence, the integral of the divergence. Okay. So instead, let's do that. We take the integral of the divergence. Well, what's the divergence? You take the derivative of the field with respect to x plus the derivative of the first component with respect to x and the second component with respect to y. Right? So it's 0, right? dx of 2y plus dy of negative 3x dA. Right? So that's just 0. So it's 0. So again, this is a contrived example to show you that it's sometimes useful to